Many data structures can be summarized as being units of data that are in some way connected to other units of data, and this can be simulated very well using the fundamental data structure called linked nodes. A node is a container for data that has one or more links to other nodes. We can implement nodes in our code with a very simple data structure called a record, which groups different pieces of information together into a single unit. By the way, I'm just going to use the general term record to describe this concept. Depending on the programming language, it might be called something different like a struct or a class. We set up a record by first defining its type by telling our code all of the different units of data it should hold, which are called its fields. An individual record can have as many fields as we want of as many different types as we want. Then we can use this record definition as a blueprint to create instances of the record, which are like copies of the blueprint that can store specific data in their fields. So a node is just a record that uses one field to store some sort of data, and at least one other field to link to other nodes. These links are actually a special data type called pointers, which store a specific address in computer memory. We can store the address of another node, which then effectively makes this field point to where that node is located. Then we can follow these pointers to traverse from node to node within the data structure. It's important to note that these pointers take up memory space just like any other form of data, which means every node will cost more memory than just the cost of its data. This is called overhead. For example, consider a simple node that stores an integer as its data in a single pointer. In many systems, the integer will take up just 4 bytes of memory, but then the pointer will be 8 bytes, giving the whole node a size of 12 bytes. In this structure, only 1/3 of the memory usage is for actual data, with 2/3 being used for overhead. Now that we understand what nodes are, let's put some together to make a linked list. This data structure is a series of nodes that are linked together in a linear fashion. Each node has 2 fields. One stores the data and the other stores a pointer to the next node in the sequence. The linked list structure as a whole stores a pointer that points to the first node in the sequence, which is called the head. We access data inside the linked list by starting at the head node, then following the next pointers continually to traverse from one node to the next until we get to a node whose data we wish to use in some way. At this point, we can just access this node's data field. While moving forward through the list is easy, we can't move backward. This is because each node only has access to its own fields, so only its data and the pointer to the next node. We have no way to see what points to the current node. In this way, pointers are kind of like one-way doors. You can go through them, but you can't come back. Because of this, we aren't able to access or traverse to previous nodes in the sequence. Or, at least this is true for a singly linked list, which has only one pointer field in each node. We could add a second pointer field to each node that points to the previous node in the sequence, which would then make this a doubly linked list. Now, traversing backward is just as easy as traversing forward. We simply continually follow the previous pointers. In some cases, this might be more useful, but it comes at the cost of having to store an extra pointer for each node. So that's how traversal works, but linked lists really shine when we start to modify them. Let's try inserting some new data. If we wish to add data to the end of the list, we'll first need to figure out which node is currently the last one in the sequence. To do this, we'll just need to traverse through the linked list until we found a node whose next pointer is null, which means it has an empty pointer instead of pointing to another node. Of course, if a node has no next node, then it must be the final node in the sequence. So we'll create a node variable, let's call it current, and start it at the head. And so long as its next node isn't null, let's update current to be the node that is being pointed to by its next field. This moves us forward in the list. Once the while loop stops, we know current must be on the final node. So now let's make a brand new node that stores new data in its data field and null in its next field, because this will be the new last node in the list. Finally, we can update current's next field to point to the new node, and we have successfully added new data to the end of the list. By the way, all of the algorithms that we're going to discuss right now are going to have a sneaky bug hiding in them. I'll get back to this later, but in the meantime, see if you can spot it. If we're going to add a bunch of data to the end of the list, it's a waste of time to always have to traverse through the entire list to find where it ends. So we often add another pointer in addition to the head that stores the tail, or the current final node in the sequence. Now adding to the end of the list is much quicker. We just need to make the new node, then access the tail node and update its next field to point to the new node. Don't forget to update the tail pointer since it should always point to the last node in the sequence. This change has improved the time complexity of adding elements to the end of the list from O of n linear time to O of 1 constant time. Just make sure to always remember to keep the tail pointer properly updated any time you insert or delete at the end of the list. To keep things focused, the rest of the examples I show are going to assume we aren't keeping a tail pointer, and therefore we don't need to maintain it. We can also insert new data in the middle of the list. For example, let's say for some reason we want to have a function that inserts a new element so it comes right after the number 2, which is already in our list. For simplicity, let's assume there's never a case when there isn't a 2 in our list. To start, we'll need to traverse to the node that comes right before where we want to add the new one. In our example, we want to add the new element right after the 2, so we'll need to traverse until we're on the 2. So let's start the current node at the head and set up a loop so it only stops when the current node's data is 2. Now, let's create our new node and store new data in its data field. Then, think about where we want this node to be in the sequence. It should be the node right before the current node's next node. So we'll set the new node's next field to be the current node's next field. Then we'll change the current node's next field to point to the new node. And just like that, we've inserted a new element in the middle of the linked list by only changing 2 pointers. Just like we can add nodes, we also should have a way to remove them. Luckily, deleting nodes is also pretty easy. If we're deleting the first node, it's as simple as moving the head pointer to its next node to skip over the first one. Remember that the head is like our entry point into the list, so moving the head past the first node makes the first node inaccessible, removing it from the list. Now, depending on the programming language, we can either manually deallocate memory for the removed node, or the system will automatically free that data for us when it recognizes there isn't anything referencing this node. This is called garbage collection. Of course, we can delete any node in the list, not just the first one. To match our function that inserted after a 2, let's write a function that deletes the node that comes after a 2. Similar to insertion, we'll traverse to the node that comes right before the one we want to delete, so we'll once again loop until we find the 2. We want to delete the node that comes right after current, so we'll update current's next field to point to the node that is 2 ahead in the sequence. That is to say, its next node's next node. This basically moves the next pointer to skip over the node that we're deleting, which completely removes it from the sequence. Now the removed node can be garbage collected. The flexibility that linked lists have with insertion and deletion is their biggest strength. They can grow and shrink to hold exactly as many nodes as needed super easily just by moving pointers around. There is a huge weakness though. To access or modify a certain node, we need to traverse to it by first going through each node in the sequence that precedes this node. This is a linear time operation, which can be quite slow, especially when compared to the constant time indexing ability of arrays, the arch nemesis of linked lists. There's a reason why we can't speedily index straight to any node in the structure, and it's due to the way nodes are stored in memory. Whenever we create an instance of a record, such as a node, the system finds any free chunk of memory that is just big enough to store all of the fields of this instance. We have no way of knowing where this memory chunk will be, except for storing a pointer that points us directly to it. This unpredictability is exactly why there's no way to quickly index to certain nodes. Even though 2 nodes might be right next to each other within the linked list, in memory they could actually be very far apart. We have no way of finding where, say, the 5th node in the sequence is, except for following the pointers from the 1st, 2nd, 3rd, and 4th nodes. Remember when I said our insertion and deletion algorithms had a sneaky bug hiding in them? Well, that bug is the infamous, the terrible, the null pointer exception. Let's take another look at our function that adds data to the end of the list without using a tail pointer. To recap, first the while loop will traverse to the node that is currently at the end of the list, then it sets this node's next field to point to a new node that holds the new data. Nice and easy. So this will add a new node to the end of the list regardless of how many nodes are already in there. Unless there are exactly 0 nodes in the list. In this case, the head will be null because there are no other nodes that it could point to. We start current at the head, so it also stores null, then the while loop checks if current's next field null pointer exception. The problem is that a null reference represents nothing, and nothing has no fields. We can't access the next field of something that has no fields, so it causes the null pointer exception. We can fix this by adding a special case for if the list is empty. We'll move the part where we create the new node to the top, and then if the head pointer is null, that means there aren't any nodes in the list yet. So we can add the new element by making the head point to the new node. If the head isn't null, then we do the traversal process just like before. Many linked list operations would require a similar special case for when the head is null. But if we want to avoid having to write these special cases, we can use a headed linked list. This means we'll add what is called a sentinel node at the front of the list that doesn't represent an element like the rest of the nodes. It's just a dummy node that is kept at the front of the list. This is where we have our head point, and the sentinel node never changes and it will always be the head. Compare this to the unheaded linked list, where the head pointer changes whenever the first node is inserted or deleted. The key difference is that now the headed linked list will always have at least one node, even when the list is empty. And the head is never null, so we can avoid having that special case in many of our functions. One adjustment we'll have to make to accommodate the new header node is to always start a traversal at the first node with real data, so we need to skip over the header. This is as simple as changing from starting at the head to starting at the head's next pointer. So headed linked lists simplify the logic to avoid null pointer exceptions when the head is null, but don't let your guard down. We're still not completely safe from null pointer exceptions. If we ever attempt to access the fields of something that stores null, it'll throw this error, so it's a good idea to always double check that what we're looking at isn't null before we access its fields. So far, all of the linked lists we've looked at have a clear beginning and end. But what if we wrapped the list back on itself, linking the last node to the first to create a loop? Now we have a circular linked list. While this would make a great symbol for the eternal cycle of life and death, it's also useful for representing repeating sequences, such as a rotating schedule. In this case, the head points to the node whose turn it is in the schedule. We can go through the cycle by advancing the head pointer forward to its next node. This can be thought of as rotating the entire sequence, like turning a dial. If we want to add something new to the schedule, we usually insert it in the position right before the head, so it will be processed after all of the elements currently in the cycle. This makes it so tail pointers are super useful in circular linked lists. We'll add new elements after the tail, then move the tail forward to point to the new node. And whenever we advance through the cycle, we move the tail forward just like the head. You might notice that the tail and head pointers are always immediately adjacent to each other, with the tail pointing to the head. So storing both pointers is a bit redundant. We can get rid of the head pointer since we can always access it through the next field of the tail node, and we still maintain the ability to super quickly add nodes to the end of the cycle by placing them after the tail node. But whether your linked list is circular, headed, singly, or doubly linked, the core idea is quite simple. Linked lists are sequences of nodes linked together by pointers. They can insert and delete elements super easily, but it's slow to access elements. This makes them well suited for situations where you need to modify the list often, but rarely need to access data. And linked lists are just the beginning. Linked nodes can be used to make countless other useful structures. Together with arrays, they form the foundation of every other data structure in computer science. So join me next time in this series as we use both linked nodes and arrays to implement two of the most commonly used data structures, stacks and queues.